We're going to see a new kind of function that's not really a function, so I'm going to put it in quotes. It's the Dirac delta function. But before we actually see it, we need to have some setup to see how it works. Consider a function that represents a short burst of constant energy. I'm going to start with the graph of such a function. On the t-axis, I'm going to mark points a and b, where b is bigger than a. And I'm imagining a function whose value is 0 between 0 and a, hits a value of 1 between a and b, and then is 0 back after b. To be careful here, I want it to be a function, so I'm going to open up the right endpoints of those segments. And what we've got is a function that is off, and then on, and then off, and when it's on, it has a value of 1. This can be expressed in terms of the unit step function. The unit step function of t minus a is 0 and then 1, 0 for values of t between 0 and a, and 1 for values of t greater than or equal to a. Drawn out, it looks like that. We're going to do another instance of the unit step function, u of t minus b, which has all of the same properties except instead of a being the delineating number, it's b. And for the graph of that, we're on the t-axis between 0 and b, and then we're up at 1 after b. The way we're going to get this to be 0 and then 1 and then 0 again is to subtract blue minus green. So we're going to have u of t minus a minus u of t minus b. This one now has three definitions. For u of t minus a, it's going to be 0 and then 1 and then 1, with our intervals being between 0 and a, between a and b, and greater than or equal to b. The other unit step function is 0 and then 0 and then 1 for those intervals. This will give values of 0, 1, and then 0. Again, for those same intervals defined by a and b. Now suppose when it hits that high peak, that burst of constant energy, its height is not 1, but some value 1 over 2a. Instead of a and b, what I'm going to do is I'm going to identify an interval on the t-axis centered at t sub 0 and with a radius of a. So the left endpoint is t sub 0 minus a, the right endpoint is t sub 0 plus a. Our function value is 0 until we hit t sub 0 minus a, and then it's 1 over 2a until we hit t sub 0 plus a, where it drops back down to the t-axis. That behavior describes the unit impulse function. It's denoted t subscript a, t minus t naught. The a is the radius of the interval over which the function is active, and the t sub 0 is the center of that interval. Delta sub a of t minus t sub 0 is 0 when t is between 0 and t naught minus a, 1 over 2a when t is between t naught minus a and t naught plus a, and 0 when t is greater than t naught plus a. Notice our intervals are closed on the left endpoints and open on the right so that we don't overlap and violate the definition of a function. For small values of a, this represents a large amplitude for a short time around t sub 0. Looking back at our graph here, we have an interval that has a width of 2a and a rectangle essentially that has a height of 2a, and so the area underneath where it's active is 1. So we can note that the integral from 0 to infinity of delta sub a of t minus t sub 0 with respect to t is equal to 1. As the size of a decreases, the height of 1 over 2a increases, but then the area under the rectangle is a constant 1. How small should we be thinking for a? Pretty small, like a tenth, a hundredth, a thousandth. I want you to think about something like a baseball being hit by a bat. And in fact, I want you to think about a diminishing and becoming 0. Now we have the definition of the Dirac delta function. Not really a function, but it's denoted delta without the little subscript a. Delta of t minus t sub 0 is the limit as a approaches 0 of delta sub a of t minus t naught. So the unit impulse function with a going to 0. Let me back up just a moment, something I kind of glossed over. We call it the unit impulse function because the area under the, when it's on, is 1 unit. Okay, the Dirac delta function has a couple of properties. One, that delta of t minus t sub 0 is defined in pieces, but it's infinity when t is equal to t sub 0, and it's 0 everywhere else. So everywhere t is not equal to t sub 0. This isn't really a function because we don't allow a function to have a definition of a value of infinity, and hence the quotes. The second property is that the integral from 0 to infinity of delta of t minus t sub 0 dt is equal to 1. Even though it's not formally a function, it does have its uses, and we can transform it using the Laplace transform. The Laplace transform of delta of t minus t sub 0 is e to the negative s t sub 0. We can think about this in contrast to the unit step function. The Laplace transform of the unit step function u of t minus a is e to the negative as over s. A couple of things here. Number one, t naught is replacing a because a had a different use in the development of the Dirac delta function, but you can think of that as essentially the same thing. And the other one is the unit step function, when we transform it, we end up with a denominator of s. Because remember, the unit step function acts as being multiplied by another function, and in this case, the other function would be 1, and its transform is going to be 1 over s. The transform of the Dirac delta function is e to the negative st naught, like, e to the negative as, but without the denominator of s. I need you to do something to remember that the transform of the delta function has no s in the denominator, but the transform of the unit step function does have an s in the denominator. I do see that get mixed up. Let's see a proof of this transform formula. We're going to start with the unit impulse function, delta sub a of t minus t sub 0. We're going to work with it and then take a limit. It's 1 over 2a times the unit step function of t minus the quantity of t naught minus a minus the unit step function of t minus t naught plus a. And the 1 over 2a is multiplying that entire quantity. The Laplace transform of delta sub a of t minus t sub 0 is then equal to 1 over 2a times the Laplace transform of the difference of the unit step functions, right? So for the first unit step function, we have e to the negative s times t naught minus a divided by s, minus, for the second unit step function, e to the negative s times t naught plus a divided by s. Notice that inside the brackets in the numerator of both of our fractions, we have a factor of e to the negative s times t sub 0. I'm going to factor that out, e to the negative s times t sub 0, and then combine the two fractions, and what we end up with is e to the negative as minus e to the negative as, all divided by 2as. In order to get the Laplace transform of the Dirac delta function, we're going to take a limit. So the transform of delta of t minus t sub 0 is equal to the transform of the limit as a approaches 0 of delta sub a of t minus t sub 0. And we have an expression to replace that with based on what we've just done. I'm going to factor out the e to the negative st sub 0, because as a approaches 0, it doesn't care about that factor. And we're going to multiply by the limit as a approaches 0 of this e to the as minus e to the negative as over 2as. this limit gives us 0 over 0, an indeterminate form. So we're going to use L'Hopital's rule, but remember here, it's the limit as a approaches 0. So when we differentiate, we're differentiating with respect to a. When we do that, and denote that we are using L'Hopital's rule, let's use good form here, we get e to the negative s times t sub 0 times the limit as a approaches 0 of se to the as plus se to the negative as divided by 2s. The s's all divide out. As a approaches 0, the numerator approaches 2, so the 2's divide out, and we're left with simply e to the negative st sub 0, which is exactly what we expected. We'll close this video out with an interesting fact, and it is that when t naught equals 0, we have that the Laplace transform of delta of t is equal to 1. Note that that is e to the negative s times 0, right? If you're not sure if that's interesting, I mean, it's interesting, right? And now I want to remind you of something that we saw at the beginning of Laplace transforms. We saw that the Laplace transform for a function f exists if f is piecewise continuous and of exponential order. We called that a sufficient condition for existence. It's not a necessary condition for the transform to exist. Here we have a function that is not piecewise continuous. I mean, it's 0 everywhere, and then it's infinity. And so that's the difference between a sufficient and a necessary condition. And I said at the time that we can have functions that either are not piecewise continuous or are not of exponential order for which a Laplace transform still exists. And this is that example. We also saw that if f is piecewise continuous on 0 to infinity and of exponential order, then the limit of the transform is 0. Again, we have a function that violates those conditions. The limit of the transform, I mean, it transforms to 1, right? That limit is not 0 as a approaches infinity. So when we encounter things that seem to violate principles that we've already established, I want you to remember that there were hypotheses, continuous or piecewise continuous, exponential order. And if those hypotheses aren't satisfied, then different things can happen.